This is Lesson C, Free Fall, for Unit 2, Motion in One Dimension, General Physics. This lesson will explore freely falling bodies as examples of motion with constant acceleration. And by the end of this lesson, you should be able to relate the motion of a freely falling body in motion with constant acceleration, calculate displacement, velocity, and time at various points in the motion of a freely falling object, and compare the motions of different objects in free fall. On August 2nd, 1971, a demonstration was conducted on the moon by astronaut David Scott. He simultaneously released a hammer and a feather at the same height above the moon's surface. The hammer and feather both fell straight down and landed on the lunar surface at exactly the same moment. Although the hammer is more massive than the feather, both objects fell at the same rate. That is, they traveled the same displacement in the same amount of time. Many years before that, Aristotle, in 384-322 BC, said that things fall because they want to regain their natural state, or earth wanted to be with earth, water with water, and so on. So a rock would fall back to earth to be with other rocks. Since a big rock possesses more earth, it would fall faster than, say, a feather. Aristotle's idea appeared to be true because a rock certainly does fall faster than a feather. In fact, it made so much sense that Aristotle's ideas on that subject were accepted as truth for around 2,000 years until the Renaissance. The first scientific study of gravity was done by Galileo, this guy right here, in 1564. He lived 1564 to 1642. He was trained as a mathematician and a university professor. In the late 1500s, Galileo conducted a series of experiments on gravity. He is supposed to have demonstrated that heavy objects and light objects fall at the same rate. The act of doing experiments to find out what would happen was a very daring idea. People had not really done experiments before. That's why Galileo is considered the father of science. Galileo did not, as it's popularly believed, state that objects would hit the ground at the same time. He understood air resistance, but he also understood that without air resistance, the objects would fall at exactly the same rate. And that was what was really novel about what Galileo did, was that he removed the idea of air resistance. Okay, now he couldn't physically remove air resistance. He didn't have the technology to do that. But he thought it through and realized that without air resisting falling objects, these objects would fall at the same rate. And we can actually try this yourself. If you find two objects of different masses and negligible air resistance, so like a rubber ball and a rock, two things that are different masses that are not going to have a lot of air resistance when they fall. You drop them from the same height, you'll see that they hit the ground at the same time. Galileo's idea that things fall at the same rate flies in the face of common sense. It seems reasonable that heavy things ought to fall faster than light ones, but that's just not the case. To study gravity, Galileo found he had to slow it down. This was because he couldn't measure the time it took an object to fall with the crude instruments of the time. Gravity was slowed down by having balls rolled down ramps, or we call them inclined planes. Gravity still caused the motion, but its effect was decreased to the point where Galileo could gather some useful data. And so he found that the distance that accelerated objects would travel was proportional to the square of the time. So nowadays, we have better equipment than Galileo did, and what we can do is we can remove air resistance in certain situations. So if we have a long tube that we're able to remove the air from inside this tube and drop a small steel ball, a guinea, it's a coin, or a feather, we drop them at the same time in this vacuum tube, we will see that they fall at the same rate and they would land at the same time because we're able to remove that air resistance. So now on Earth, gravity exerts a force on everything with mass. So a force, which we're going to learn about in our next unit, forces are pushes and pulls. Okay, so everything on Earth is under the force of gravity. This force makes all objects accelerate downwards towards the center of the Earth. This acceleration it varies a little bit depending on where you are. At the North Pole, it's a little higher than when you're at the equator. Okay, because Earth is not a perfect sphere. Fortunately, we can pretty much ignore the tiny differences in acceleration of gravity. The value which is commonly used for this acceleration is 9.8 meters per second squared. Gravity's acceleration is kind of special, so it's given its own little symbol, g. Okay. If we drop a rock from the top of a cliff, in 1 second it will reach a speed of 9.8 meters per second. After 2 seconds it will be traveling 19.6 meters per second. In 3 seconds it's going to be going 29.4 meters per second. At 4 seconds it will be at 39.2 and so on. So it looks like the rock will keep going faster and faster and faster until it smashes into the earth. And it would if it were falling in a vacuum. The thing is that air causes a frictional force that opposes the rock's fall and it slows it down. For short drops with dense objects like rocks, we can reasonably ignore the effects of the air. The scientific term for this force exerted by the air is drag or air resistance. Sometimes it's called wind resistance. At really high velocities over long distances, the drag can become pretty significant, especially for objects that are not dense, like feathers or leaves or fluff. In the real world, an object in free fall will accelerate to its terminal velocity. Terminal velocity is the speed at which the force of gravity equals the drag force. The object then stops accelerating and falls at a constant velocity. People jumping out of airplanes experience this. They typically laid out position that skydivers use gives them a terminal velocity of around 100 miles an hour. So when an object is released and allowed to fall, its motion can be described by this table right here. In 1 second, it's going to be going a velocity of 9.8 meters per second. It will have traveled a distance of 4.6 meters. After 2 seconds, 19.6 meters per second, gone 19.6 meters. After 3 seconds, 29.4 meters per second, it will have gone 44.1 meters, and so on. All things in free fall then accelerate downward at this rate of g, 9.8 meters per second squared. Simply means that as a thing falls, its velocity will change by 9.8 meters per second every second that it falls. We can use the constant acceleration equations that we developed in the last video to describe the motion of falling objects. However, instead of using x as our position, we use y for acceleration. We use g instead of a. So therefore, those acceleration equations become this, where instead of using a, we just replace that with g. Instead of using x, we replace those with y because we're working in the vertical direction. Our vertical axis is y. Now, also notice that instead of VF equals VI plus AT, it's VF equals VI minus GT. This minus is a directional. This G has a value of 9.8 meters per second squared. It's a vector. Accelerations are vectors, so it has a direction downward. So we always use a negative in these cases because it's negative G. Okay, it's negative 9.8 meters per second squared. Now, does this mean that the object is decelerating? Does it mean it's slowing, or does it mean that the object is moving along a negative axis? For an object falling along the y-axis due to gravity, it means the object is accelerating, but in the downward direction. So let's try to make a sense of this. Let's look at a motion diagram of a ball being tossed straight up and then falling back down. So try it first. Toss a ball straight up and catch it. That's the motion we're looking at. Here is a motion diagram of such a thing. From this diagram, we can see that as the ball rises to its highest point, it slows and the acceleration points downward. As the ball comes back down, it speeds up and the acceleration points downward as well. For an object in free fall, the acceleration always points downward with a magnitude of 9.8 meters per second squared. Now that's a very important point. As an object, any object in free fall always has an acceleration of g pointed downward, 9.8 meters per second squared pointed downward. Here are some other important points summarizing this type of motion. The velocity is first upward and then downward. So our velocity vector and acceleration vectors first point in opposite directions on the way up, and then they point in the same direction on the way down. Acceleration, again, always points downward. The distance up, the amount of distance it takes to go up, is equal to the distance down. This is for an object that you've tossed straight up in the air and it comes back down to that same point. Okay? The launch speed, the speed at which that object is launched, is greater down here at the bottom, right? Because it slows as it goes up. The launch speed is equal to the speed just before landing. Okay? So at the moment just before catching that ball, the speed is equal to the same speed at which it was launched. It's just pointing in the different direction. Okay? The speed at the highest point right up here is 0 meters per second. It doesn't mean that the ball goes up and stops and then comes back down. It just sort of passes through 0. Okay? And finally, the time that it takes for the ball to go up is equal to the time it takes to go down. So if it takes 1.25 seconds to go up to this highest point, it'll take 1.25 seconds to get to the back to the starting point for a total of 2.5 seconds. This graph here shows the velocity of the ball. So again, a ball tossed up and back down to the same point. This is a VT graph of tossing a ball straight up and back down. As you can see, there's an instant where this velocity of the ball is equal to 0 meters per second. This happens at the instant when the ball reaches the peak of its upward motion and is about to begin moving downward. Although the velocity is 0 at the instant the ball reaches this peak, the acceleration is still equal to 9.8 meters per second squared down. At every instant, regardless of the magnitude or direction of the velocity, it's important to note that the acceleration is this negative 9.8 meters per second squared, even at the peak where the velocity is 0. The straight line slope of this graph indicates that the acceleration is constant for every moment. So what we can get out of this graph, just like with position time graphs, we can get the velocity from the slope of a position time graph. We can get the acceleration from the slope of a velocity time graph. Okay, so we can see that this thing began with a velocity slightly more than 10 meters per second. It went up, it passed through 0. What happens right here also is that our object changes direction. Okay, on a VT graph, anytime the line passes through 0 here, the object has changed direction. So this is all negative velocity down here. This is all positive velocity up here. Positive direction, negative direction. And this graph also indicates, notice how it goes further than the 10 meters per second that it started with up here. So this is actually an object, this is depicting an object that has gone up and then back down further, like this. Okay, so let's look at an example. We've got Jason hits a volleyball so that it moves with an initial velocity of 6 meters per second straight up. If the volleyball starts 2 meters above the floor, how long will it be in the air before it strikes the floor? So let's start by looking at what we know. So we know that our initial velocity is 6 meters per second. We know that our acceleration is going to be this negative 9.8 meters per second squared. So let's look at what this ball is going to do. We've all seen a volleyball get hit. It goes up and it comes back down to the floor. He's hitting this ball 2 meters above the floor. So this ball is going to go up and then it's going to come back down. Okay? So this is a situation where the ball is going to go to a certain height and then back down further than it originally did. So it's going to look something like this. Okay? Let's analyze what's going to happen. So at this point right here where it launches, that velocity is 6 meters per second. Okay? The velocity at this point right here where it's at its highest point is 0 meters per second. Okay? So what we're going to have to do is kind of split this into a couple of different problems and then put things all together. We're going to have to look at this motion up first to this point where it's 0 meters per second. And then we'll have to look at this motion downward and figure out how long it takes to do this first, and then how long it takes to go back down. Okay? And then add those together. Okay, so using this kinematics equation, we can figure out how much time it takes for the thing to go up to its highest point. We put in 0 as VF here because that's the velocity at this highest point. Our initial velocity, acceleration, and we end up with a time of this 6.1 or 0.61 seconds. That's how much time it takes for the thing to go to this highest point. Now, the thing is, we want to figure out how much time it takes to go down. The problem is, we don't know how high it is. We do know that from this point right here where it was launched to the ground, that's 2 meters right there. Okay, so that's 2 meters there. But what we don't know is how high it went. So we have to figure that out first. To do that, we're going to use this our fourth kinematics equation. Okay, so this is how it would look when we do our substitutions. We end up with a height of 1.84 meters. Now this is the height above launch point. Okay, so if we want to know the total distance from where this velocity is 0 at the top to the bottom to the floor, we have to add the 2 meters into that, which is going to be this 3.84 meters. Okay, so from this highest point to the floor is 3.84 meters. It already took us 0.61 seconds to get here. Now we're going to think, okay, if this ball were dropped from this height here, this 3.84 meters, to the floor, how long would that take? And then we're going to take those two times and add them together. So to do this, what we're going to use is our second kinematics equation, YF equals YI plus VIT minus 1/2 GT squared. Now when we go to substitute in, one thing that's very important to realize here about this VI, this is not the 6 meters per second that we began with, because look at this little diagram. The 6 meters is down here. We're looking from this perspective here where the velocity is 0. So in this case, what we're going to be using is we're going to substitute in 0 for this VI right here. So it looks like this, where we've got our 3.84 for our initial height, 0, that's the floor, so our final position is 0. Initial velocity is 0 because we're acting as though we are dropping this ball from this point up here. And then, of course, 9.8 for our acceleration. So when we go to solve this, here's what we end up with. We end up with this 0.89 seconds. So now we've got two times that we have to add together to get our total time. So our total time will equal time 1 plus time 2, for a total time then of 1.5 seconds. Okay, so that's one type of free fall question that we can see, right? There are kind of three types of free fall questions that we might look at. One would be you've taken an object and you just drop it straight down. There's the first type. Second type is you take an object and you toss it up and it comes back down to the same height. And then there's this type that we just looked at where we're going to have an object that goes up and then goes back down further than where it was launched. So go ahead and stop here. Do number 2 and 3 out of practice F in your notebook. Okay, so there you go. And we will see you in class.